Hello and welcome to another video in Ch 101. In this video, we'll be discussing the extent of reaction, a lesson in Calc, which is a topic under the fundamentals of stoichiometry. So the outline of this video, we will be having a problem, and then we will discuss first the theories related to that problem, the general balance equation, and the extent of reaction. And then we'll try to solve the problem. First the outline and then the complete solution. Finally, we will summarize the solution that we made for the problem. All right, so problem agad. Problem statement, a stream containing 80% mole of chlorine gas and 20% mole of methane gas is fed to a reactor. Methane reacts with chlorine gas and oxygen gas in air to form hydrochloric acid and carbon dioxide. The product stream contains 27.3% mole of hydrochloric acid and 25% mole of methane fed remained unreacted. The problem asks for calculate the moles of hydrochloric acid in the product stream per 100 moles of feed, and second, the percent excess of air fed using the extent of reaction method. All right, so it's evident naman in the problem that we'll be using the extent of reaction, but let us recall first the general balance equation. So in the general balance equation, whatever we input and whatever we generated, that should be equal to the output plus the consumption plus the accumulation in the system. If the system is in steady state or if the process is in steady state, there will be no accumulation. So the input and generation would be equal to the output and consumption. Now, in the extent of reaction method, when solving stoichiometric problems, it basically asks by how much did the reaction proceed? Or better yet, to what extent did the reaction proceed? Kaya ang extent of reaction. Meaning, we will be assigning a value. For example, the commonly used notation is epsilon. If we have multiple reactions, maybe we could use epsilon sub 1, epsilon sub 2. But these values, these epsilon values, basically measure the extent by which a reaction happened in a process. So going back to the problem, for the solution, in the given, I already draw the process flow diagram. So again, the problem states that the feed has 20% mole methane entering and 80% mole chlorine gas entering a reactor. And then the product stream has 27.3% mole of the hydrochloric acid. And then it was also said that methane did not react completely. It was not used completely. 25% of the ethane fed was unreacted, meaning it will exit through the product stream. So we have methane in the product stream, which is 25% of the methane fed. And then we'll have other components in the product stream, which I have not written yet for now. And then finally, the methane reacts with chlorine gas and oxygen gas from air. So there's an air stream entering, a stream of air entering, which is composed of 79% nitrogen gas and 21% oxygen gas. And then we are required the following. First, the mole of hydrochloric acid produced per 100 mole of the feed. And second, the percent excess of air. All right, here's the process flow diagram again. And the first thing that we can do in the solution is to set a basis. Now, for convenience, since the problem asks for, what's that again? Moles of HCl per 100 moles of feed. So that's a convenient basis then. We can set the basis as 100 moles of F. And since F is 80% mole chlorine gas, we'll have 80 moles of chlorine, 20% mole of methane, then that's 20 moles of ethane in F. And then the given also said that the methane gas reacts with chlorine gas and oxygen gas from air to form hydrochloric acid and carbon dioxide. So we can write the reactants and the products and then just balance the equation. And you can check later in your own time that the equation is balanced. So based on this reaction, based on this balance equation, we can already get the limiting reactant. Since we have 80 moles of chlorine gas and 20 moles of methane, from the balance equation, the mole ratio is 2 moles of chlorine gas reacts with 1 mole of methane. Then that means that 20 moles of methane will require 40 moles of chlorine gas only, meaning chlorine will be in excess. So methane, that's the limiting reactant. And this is important because we'll be using this to identify which component or which of the two, chlorine or methane, determines the theoretical oxygen. Alright, so the next part of the solution, first I looked into the components of P using the extent of reaction method. So the one that we know in P, this is hydrochloric acid. And based from the reaction, 4 moles of hydrochloric acid is produced if we have 1 mole of methane. So we'll take a basis of 1 mole of methane here. So 4 times epsilon is equal to the moles of hydrochloric acid in P. For methane, that would be the original amount of methane, 20, minus however much was consumed in the reaction. And we set that as the epsilon. So 20 minus epsilon is equal to the moles of methane in the product stream. We also know that 0.25 or 25% of the methane fed is in the product stream. So 25% of 20 is 5. Later on, we can solve for E. 20 epsilon. 20 minus epsilon equals 5. Next component of P, chlorine gas. So originally, we have 80 chlorine gas, and the reaction would require 2 moles of chlorine gas per mole of methane. So 2 times epsilon. That's equal to 80 minus 2 times epsilon. That would be equal to the moles of chlorine gas remaining in the product stream. Next, carbon dioxide. Carbon dioxide, the reaction would produce 1 mole of 1 mole of carbon dioxide per 1 mole of methane. So however much methane used, that's also the amount of the moles of carbon dioxide produced. So epsilon is equal to the mole of carbon dioxide in P. And then finally, the components from air. For nitrogen, we don't know yet since air is fed in excess. So however much nitrogen gas is fed, that's also the nitrogen gas in P because it didn't react with the with methane, or it didn't react anywhere in the reactor. Now for the oxygen, 1 mole of oxygen is used for every 1 mole of methane. So however much oxygen is fed, NO2 fed, minus epsilon, the remaining would be the oxygen that exits in P. And then again, we can already solve for epsilon from the extent of reaction in methane. So 20 minus epsilon equals 5, and we'll get epsilon equals 15. And then we can answer already the first question. The first question asks for the moles of hydrochloric acid in the product stream. Here, 4 times epsilon is equal to the moles of hydrochloric acid. And that would be 4 times 15. So we have 60 moles of hydrochloric acid in the product stream. And similarly, we can solve for the chlorine gas and carbon dioxide gas. So 80 minus 2 times 15, that's 50 moles of chlorine gas in the product stream. And then 15 moles of carbon dioxide in the product stream. Okay, so we already have the moles of hydrochloric acid, and initially we are given that the product stream 27.3% mole of the product stream is hydrochloric acid. So since we know that this is 60, so 0.273 P is equal to 60. We can solve for the moles in the product stream, and we'll get this value, 219.78. Now, the moles of nitrogen and oxygen in the product stream, we can get the total moles of them by subtracting the sum of these 4, since we know these 4. If we subtract the sum of these 4 from the moles of the product, which we already got here, then we'll get the total moles of nitrogen and oxygen in the product stream. And that will be 219.78 minus the sum of 5 plus 60 plus 15 plus 15. And we'll get 89.78 moles of nitrogen and oxygen in the product stream. Now, this is relevant because we'll be using this to calculate now for the percent excess of air, percent excess air. Here, if we let x equals excess air as a fraction, for example, if the excess air is 10% in excess, then x is 0.1. Or if it's 15% in excess, then x is 0.15. That's how I use this notation. But you can use, however, whatever is comfortable with you. You can even use the excess air as in the moles already. So later we can check if there are other solutions. So again, the moles of oxygen in P plus the moles of nitrogen is P is equal to 89.78. We got that here. And then 1 plus X times the moles of oxygen theoretical minus the moles of oxygen reacted. That's the total moles in P. This line above. Plus 1 plus X times the moles of oxygen theoretical times 79 over 21. That's the moles of nitrogen in P. Now we got 1 plus X because 1 that represents the theoretical oxygen, and then plus the excess plus the fraction of excess air, X. So 1 plus X. And then for nitrogen, we multiply the theoretical oxygen by 79 over 21 since in air that's their mole ratio, 79% nitrogen, 21% oxygen. And then the sum of moles of oxygen in P plus the moles of nitrogen in P, that will be 89.78. So substituting the moles of oxygen theoretical, I got this as 20 from the reaction. Since there's 20 moles of the limiting reactant methane, and the methane and oxygen has a 1:1 ratio. So the theoretical oxygen would be 20 moles then. So 1 plus X times 20 minus the moles of oxygen reacted, that's 15 moles of oxygen reacted since 15 moles of methane reacted din, di ba? And 1:1 ratio again. So 15 moles of oxygen reacted. Plus for nitrogen, that's 1 plus X times 20 times 79 over 21. All of that is equal to 89.78. And from here, we can get X. Solving for X, we'll get X is equal to 0.10, 0.10. So that's the final answer already. Air is fed with 10% excess. Alright, here's the complete solution in case you want to take a picture or you want to review any part of the solution. Summary for the solution in that problem. The first thing that we did is to draw the process flow diagram and to set the basis. And then we balance the reaction. This is very important. If the step here has mistakes, then the entire solution will be erroneous. Balancing the reaction and then identifying the limiting reactant, because the limiting reactant will determine which component determines the theoretical oxygen. And then after identifying the limiting reactant, we write the extent of reaction expressions for each component of P. This is to solve for P and its components. And then once the components of P are identified, we can now solve for the oxygen and nitrogen in P, which are the last components that we will be able to calculate. And in solving oxygen and nitrogen in P, that would require the theoretical oxygen. And then finally, we can set up the equations in order to solve the excess air. That ends the lesson for extent of reaction in Chicago. If you have any question, you may contact Chen Academics through these contact information. Thank you for listening and see you in another video.